Hey, all. Today we're going to be talking about equilibrium. Okay. Now, equilibrium is a special circumstance in chemistry. All right. And basically, the word itself, equilibrium, basically means balance. Technically, it is the exact balance between two processes, one which is the opposite of the other. Now, sometimes you can have what is known as static equilibrium, like when you have perhaps a rock balanced on a pinnacle, or or something like that, where something is in balance. Or you can have a dynamic equilibrium. Now, dynamic equilibriums are when, like this, when you have two processes, two things that are occurring at the same time, but in opposite directions. Okay. Now, with chemical reactions, most chemical reactions go to completion. In other words, they proceed until one or all of the reactants are used up. Think of a candle, all right? You light a candle, the candle will keep on going until either you remove the oxygen by snuffing it or it runs out of wax. But it does go to completion. However, other types of chemical reactions appear to stop before any of the reactants are completely used up. All right. Now, these reactions achieve what is known as chemical equilibrium. Now, this is a dynamic state where the concentrations of the reactants and products remain constant over time as long as the conditions are not changed. All right. And that's what we're going to be talking about today. It's this concept of chemical equilibrium. I'll give you an example. You have water that can react with carbon monoxide to produce hydrogen gas and carbon dioxide. But when this reaction occurs, it appears to stop part of the way through. All right. And just to give you an example, um, let's say you start off with equal numbers of moles of water and carbon monoxide. That's what's going on over here. Okay. Let's get the pointer on here. That's what's going on over here. You have an equal number of water and carbon monoxide COs. Now they start to react together. Okay. Boom, they start the reaction. And some of the products, in this case, the hydrogen and the carbon dioxide, are formed. Now, the reaction continues as time passes and more reactants are changed to products. But after a while, although time continues to pass, the numbers of reactant to product molecules are the same as they were back here. So the reaction appears to stop. No further changes are seen as time continues. The system has reached equilibrium. Now, to give you this in terms that you may understand, think of chemical equilibrium or any type of dynamic equilibrium to be think of like walking on an escalator, but instead of going in the same direction as the escalator is going, imagine that you're walking down an up escalator, or perhaps you're on a treadmill, right? I'm sure at some point or another, we all have gone up a down escalator or vice versa. Now, when you first get on the escalator, you're going faster up than the escalator is going down. So you are climbing up. But if you were to slow down so that you're walking up at the same rate as the escalator is going down, from the side, it would appear like you haven't moved, that you're staying in the same place. All right. Same thing if you're on a treadmill. If you are going the same speed forward that the treadmill is going backwards, your position remains constant. That's all that's really happening with a chemical equilibrium. The forward reaction is occurring at the same rate as the reverse reaction. All right. So, how does this occur? Well, let's say you have up here a high amount of concentration rate for the forward reaction, and it starts to occur. Well, as soon as it starts producing hydrogen and carbon dioxide, they start combining together. They have enough energy, they bunk into each other, and they start producing water and carbon monoxide. All right. So as soon as the forward reaction goes, then the reverse reaction occurs, and you start producing the original reactants. And it goes one way, goes the other way, goes one way, and they both start occurring. Now, when it first starts off, all right, this is the key thing. When it first starts off, we know and we've learned in previous units that reaction rates are changed by concentration. The higher the concentration, remember, the more particles there are, the more collisions you're going to have, and therefore the faster the chemical reaction rate. So, as concentration goes up, reaction rate goes up. We learned this. So, as the reactions proceed, the reverse reaction speeds up. Why? Because its reactants are increasing in concentration. All right. In other words, as this is going, we're getting more and more, as the original reaction goes, we're getting more and more hydrogen and carbon dioxide. Since those are the reactants for the reverse reaction, that reaction is increasing in speed. That's why you see it going up there. All right. At the same time, the forward reaction, the water reacting with carbon monoxide, it starts off going fast, right? Because they have a lot of reactants. But as it starts to get used up, it slows down. All right. So the forward reaction starts to slow down. So the forward reaction slows down, the reverse reaction speeds up. And they start to speed up and slow down until they end up going the same rate. All right. So it's kind of like you're going up the down escalator quickly. All right. But you start slowing down and the escalator starts to speed up until you guys are going the same speed. Once the speeds match, that's when it's in equilibrium. So when the reaction rates of the forward and reverse reactions are equal to each other, the reaction has achieved chemical equilibrium. All right. Hopefully this makes sense. All right. Big concept to get here, but it's a very important one. And we're going to see how this concept of dynamic equilibrium works in the activity dynamic equilibrium. But a few things to note about it. First of all, a reaction at equilibrium is indicated by a double yield arrow, either by a single arrow that has two arrowheads on it, or by a reaction arrow like this, where you have one forward and one reverse. For example, what you see here. Now, another thing to keep in mind, and this is something that people don't quite get sometimes, at equilibrium, both the forward and reverse reactions continue to occur. Even though from the outside they look like they've stopped, they haven't. They are still occurring. All right. Just like from the outside, if someone's not watching your feet, it may look like you're standing in the same place when going up a down escalator. But if you can actually see the feet and the escalator, the feet are still going up, the escalator is still going down. It's just from the outside, it looks like it has stopped, but it hasn't. Same thing with a chemical equilibrium. The forward and reverse reactions are still occurring. All right. And something else that people don't quite grasp. Once equilibrium is achieved, the relative amounts of the reactants products are not necessarily equal. Okay? Once it achieved equilibrium, the amount of hydrogen and carbon dioxide doesn't necessarily have to equal the amount of water and carbon monoxide. Thinking that they have to be equal is saying, like, well, the only way that you're going to be able to reach equilibrium going up a down escalator is exactly in the middle, halfway up and halfway down. But that's not true. You could match your speed close to the bottom, all right, and be most of the way down. And that would be like you have a lot of product and very little reactant. Or you could be going fast, fast, fast and get up right to the top and then slow down so that you're right up at the top. All right. That's like saying you have a lot of reactants and very little products. All right. It doesn't necessarily mean that you have to have equal amounts. You could stop in the middle. You could stop near the top. You could stop near the bottom or anywhere in between. The relative amounts are not equal necessarily. Okay. It's the rates, the reaction rates that are equal. And that exact ratio of products to reactants can be calculated mathematically. Now, this is known as the equilibrium position. Equilibrium position is the particular set of equilibrium concentrations of all the reactants and products in the chemical system. All right. In other words, where you stop, as it were. Are you close to the bottom, close to the top, somewhere in the middle? That's known as your equilibrium position. What we are going to focus on in the next section here is this concept here. If conditions that affect reaction rates change, then the equilibrium position can also change. Remember back to what changes reaction rates? All right, things like concentration, temperature, surface area, things like that. Well, if any of those change, it's going to change the equilibrium position. It's going to alter how much reactants and products you're going to have. That is important, and that is what we're going to focus on in the next section. Now, before we actually go and learn about how the equilibrium system is going to be shifting, first, I want to actually get into the math, as it were, okay? Because there is a way of predicting exactly where the equilibrium position is going to be using mathematics, all right? And that's what I'm going to be showing you guys next. Now, this is known as the equilibrium constant, or KEQ, all right? Now, the equilibrium constant is where you have the concentrations of the reactants and products can be determined using the law of chemical equilibrium. All right. Now, what this is a mathematical expression. It's a general description, but it's a mathematical expression of the equilibrium condition. It defines the equilibrium expression. All right. And basically, it's like this. Now, let's say you have a generic chemical reaction. Chemical A reacts with chemical B in equilibrium to form chemicals C and D. Now, the uppercase letters represent what the chemical formulas are. The lowercase letters represent the coefficients. Once you balance the equation, the little a, little b, little c, and little d represent what the numbers are in front, what the coefficients are. Well, if this is the generic equation, then this would be the equilibrium expression. KEQ, which is a constant, all right, it's just a number, is going to be equal to, now remember, the brackets around a substance indicates the concentration measured in molarity, moles per liter, all right? But the concentration of chemical C raised to the power of its coefficient, that's the little c, times the concentration of D raised to the power of its coefficient, divided by the same thing but with the reactants A and B. Notice how it's always the products over the reactants, okay? Now, the definition of it that I've just described is right here. It's the mathematical product, means you multiply, of the concentrations of the products raised to the power of their coefficients, divided by the mathematical product of the concentrations of the reactants raised to the power of their coefficients. And all the concentration units are in molarity, or moles per liter. All right. Now, notice how this is equal to the KEQ. This is the equilibrium constant. And that's the value obtained when the equilibrium concentrations of a chemical species are substituted into the equilibrium expression. In other words, you calculate it once you take what the concentrations are and plug it into the previous equation. When writing equilibrium expressions, please note that you only include reactants and products that are gases or aqueous solutions. So you have to look at the state of matter. Since solids and liquids do not have concentrations, they're constant, you do not include them in the KEQ expression. For example, if water, liquid water, reacts to form hydrogen gas and oxygen gas in this equation, then the equilibrium expression, all right, would be KEQ is equal to the products H2 times O2. However, normally we would divide by the reactants, but since the reactant is a liquid, it's not included. So the KEQ would simply be H2 concentration times O2 concentration. Now, please note, the H2 concentration is raised to the power of the coefficient of H2. That's why it's squared right there, okay? So the equilibrium expression is that. Now, there's going to be a video indicating how to do these problems. It's a sample problem video, and there's a couple sample problems that I want you to please try and make sure you get it into your lecture notes. Now, once you're done with that, the last thing to keep in mind is that the value of KEQ for a system can be calculated from a known set of equilibrium concentrations. So the problems you're going to get, I'm going to give you the concentrations of the reactants and products at equilibrium. You plug them into the formula and you calculate KEQ. Some of the problems, though, if I give you the KEQ and all but one of the concentrations using algebra, you should be able to rearrange the formula, rearrange the equation, and solve for the unknown. All right. I've given you a sample problem video of that as well. Hi, this sample problem video is to help students with equilibrium problems dealing with KEQ. Now, this particular one, we're going to be solving for KEQ. The chemical reaction equation is right here. N2 plus 3H2 in equilibrium with 2 NH3s. I have the concentrations of N2, H2, and NH3, and we're going to need to have the KEQ. So the first step is to take the chemical reaction equation and put it into a equilibrium expression. All right. And remember, for that, it's always products over reactants. And so we have KEQ is equal to the concentration of NH3, which is a product, raised to the power of its coefficient, in this case 2, divided by the concentration of N2. There's no coefficient, so there's no exponent, divided by the concentration of H2 cubed because of the coefficient 3. We now plug in the amounts, 1.57 squared divided by 0.921, all right, and then divided by 0.763 cubed. All right, now on my calculator, I am going to go ahead and just do this. So 1.57 squared on my calculator is right here. All right, divided by 0.921, divided by, because it's also on the bottom, 0.763 763 raised to the third power. So I'm going to use the caret 3. And I go equals, and there is my KEQ. All right. So I have, the answer is, since we have 3 significant figures in all this, it's simply 6.03. And that is my KEQ. Now for another type of problem, this is where, in this particular problem, we have the KEQ is given to us, and it is asking for the concentrations of Cl2. Here is the balanced chemical equation. As it turns out, there are no coefficients, so it makes it a little bit easier. Again, KEQ is equal to products over reactants. So the concentration of Cl2 times the concentration of PCl3 divided by the concentration of PCl5. Now I'm including all of it because just like the last one, all of them are either gases or aqueous solutions. So now I want to solve for Cl2. So that means I'm going to be multiplying both sides by PCl5 and dividing by PCl3. Those cancel out, leaving Cl2 is equal to this formula over here. So plugging in what I have, PCl5 is found to be 6.70 times 10 to the negative 3. KEQ is 8.96 times 10 to the negative 2, all divided by PCl3 on the bottom, which is 0.300. And when I plug all that into my calculator, I have 6.70 times 10 to the negative 3 times 8.96 times 10 to the negative 2 divided by 0.300 equals. And there's the number. I'm going to put that into scientific notation the easy way. And I have 2.00, because all three have 3 significant figures. Though technically, you don't, since KEQ is a constant, you don't really look at that. And it's simply 2.00 times 10 to negative 3. Since it's a concentration, it is molar. So I would say the concentration of Cl2 is equal to 2 times 10 to the negative 3. Circle that, and now I'm done. I hope you found this to be useful. Remember, if you have questions, please come to tutorial. Now, the last thing is you can get an idea of, basically how far up the escalator you are simply by looking at the KEQ expression, the value of the KEQ. So if the KEQ is a large number, bigger than 1, that means you're going to probably have an equilibrium position that's far to the right. In other words, you're close to the top of that escalator, and you're going to have more products than reactants. If the KEQ is less than 1, then the equilibrium position is the opposite. It's far to the left, and you're going to be close to the bottom of that escalator, and you're going to have more reactants than products. And if the KEQ is equal to 1 or very close to it, that usually represents a relatively equal amount of products and reactants. In other words, you stopped on the escalator somewhere in the middle. Well, I hope you found this useful. And remember, I have tutorials if you have any questions. Thank you very much.